Hi class. Next I'd like to discuss boundary layer theory. I'd like to talk about the example we introduced in discussing singular perturbation theory, the second order linear differential equation epsilon d squared y by dx squared plus a of x dy by dx plus b of x y equals 0. We're assuming here that the a and the b are functions of order 1. We're assuming epsilon is some parameter, which is we're going to set to go to 0 from the positive side. We can always arrange that by reassigning what we mean by a and by b. We can always make the coefficient of the first term a constant. We're going to set the interval we're interested in to 0 to 1, but that's not really a restriction. We can just rescale x to have the and shift our coordinate system to have the boundaries between 0 and 1. We're going to take a boundary condition, y of 0 is some arbitrary value a, y of 1 is an arbitrary value b, and we're going to consider the case where a capital A of x is strictly positive inside the interval. We saw last time that what we expect is there's actually going to be a boundary layer near x equals 0 where the function varies very rapidly, and there's going to be a region outside for x away from 0 where the region varies where the solution varies more smoothly. So schematically, if we look at the solution, we expect there's going to be an inner solution here, which is valid for small x, and we expect there's going to be an outer solution which is valid for large x. And the strategy we're going to use is to figure out what is the approximate differential equation in the inner region. What we'll show is in the approximation in the inner region, the first two terms balance one another, and the third term is negligible. And we're going to find an approximate solution in the outer region. In this region, the differential equation is smooth, and the second and the third terms balance each other, and the first term is irrelevant. We're going to solve for these two solutions, the inner and the outer solution, and we're going to patch these two together in a way that we will define, so that together we get an approximate solution that covers both the inner region, the boundary layer region, and the outer region where the function varies smoothly. So let me show you how this works in practice. Let's say the boundary layer we expect has some thickness delta, and we don't yet know what delta is, so we're taking delta to be the thickness of the inner region. The problem with a boundary layer is that there are various parts of the solution that are varying rapidly, and it's hard to understand how the different sizes, different parts of the equation, different terms in the equation scale as you vary in the inner region. So we're going to change our coordinates by rescaling and defining an inner coordinate, x of inner, or capital X, which is just x over delta. And what we expect is if we rewrite things in terms of capital X, that everything in the inner region is going to vary. All derivatives, for example, with capital X, with respect to capital X, should be terms of order 1. Little x, our original variable x, is capital X times delta. If we plug it into the equation, we see that in terms of capital X, all of these are capital X's. In terms of capital X, the first term is epsilon over delta squared, d squared y by d capital X squared, plus a over delta, dy by d capital X, plus b of x y equals 0. If capital A and capital B of order 1, we see that the second term, a of x over delta dy by dx, is much greater than b of x by y, and the limit delta goes to 0. We've scaled things, so we expect the derivative dy dx is of order 1, we expect y is of order 1, b is of order 1, a is of order 1. So the only difference between the second and the third terms is the second term has a 1 over delta. Therefore, in the inner region, we're going to expect that the dominant balance in this differential equation is the sum of three terms equals 0. In this inner region, we're going to expect that the first term and the second term dominate over those two. If that's true, then the coefficient epsilon over delta squared of the first term has to equal the coefficient 1 over delta in the second term. So we find that the boundary layer thickness delta is of order epsilon formally. And the equation for the inner solution, where the solution is varying rapidly, is the second order equation, d squared y inner d capital X squared plus a of x dy inner d capital X equals 0. Here, a of x is a of delta times little x. We're interested in the limit delta going to 0, so we're going to approximate a by a constant, its value at 0, alpha, and treat it as a constant. If we treat it as a constant, this inner equation is really easy to solve. Y inner is some constant c1 plus another constant C2 times e to the minus alpha capital X, which if we rewrite in terms of little x is C1 plus C2 e to the minus alpha x over epsilon. And here we have the rapid variation that we expected in the boundary layer. Now, the boundary layer is on our left-hand side, so we can impose the boundary condition at y equals 0. At y equals 0, its value, which is C1 plus C2 from this equation, has to be equal to capital A. Now, that's going to tell us the inner solution. We have one condition on two unknown coefficients. We're going to have to figure out more to actually get the complete solution. We're going to have to figure out the outer solution. We're going to have to figure out how to determine the last unknown coefficient in the inner solution. Well, the outer solution is the solution where things vary smoothly, where we really think things are going to be determined by the balance of the second and the third equations, so terms in the equation. So a of x dy of the outside plus b of xy on the outside equals 0. Notice I haven't rescaled here. I haven't rescaled x here. We expect everything to be of order 1 in the outer region. This is a first order differential equation which I can solve just by direct integration, by an integrating factor. And the solution is y outer is equal to, it's a first order equation, so it has only one unknown coefficient. Y outer is some constant times e to the minus the integral from 0 to x, b of x prime over a of x prime dx prime. The primes are just to remind me that this x prime is a dummy variable of integration. I integrate 0 here is an arbitrary endpoint. This will be convenient. I can redefine it from 0 to something else by redefining what I mean by this coefficient c. Now, we have a boundary condition in the outer region that y at x outer at x equals 1 has to equal b, so that tells us what this coefficient c3 is. C3 is b e to the integral from 0 to 1 b of x prime over a of x prime dx prime. So y outer, if I multiply b times that's if I multiply c3, which is this, times the solution, y outer is b times the integral from 0 to 1 from here minus the integral from 0 to x from the solution of b of a integrated with respect to x prime. But the difference between the integral from 0 to 1 the integral from 0 to x is just the integral from x to 1. So the outer solution is of the form b e to the integral x from x to 1 b over a integrated with respect to x prime. So we know y outer, and we actually know it completely in terms of its boundary condition b. We have one boundary condition of 2 for the inner solution. We need one more condition to determine C1 and C2 in the inner solution completely. And this is where matching comes in. Remember that what we want to do is we want to extract the behavior of the outer solution as we go towards 0 with the inner solution as the inner variable gets large. And so formally what we're doing is we take the limit as little x goes to 0 of the outer solution, which is you're going to the left-hand endpoint, should be the limit as capital X, this inner variable, goes to infinity, because it's going far away from the left-hand endpoint, from the inner solution goes to infinity. So we're matching the behavior as the outer solution goes to 0 with the inner solution as it goes to infinity. We can compute that. The limit as x goes to 0 of the outer solution is just easy to calculate from up here. It's b times the integral, b times e to the integral from 0 to 1 of b over a dx prime. The limit as x over epsilon goes to infinity of y in, the inner solution is right here. And remember, this is where alpha greater than 0 comes in, because if alpha is greater than 0, then e to the minus alpha capital X goes to 0 as x goes to infinity. So the limit of the inner solution as capital X goes to infinity, or x over epsilon goes to infinity, is just C1. So that has to equal the outer solution as x goes to 0. This is, that is, they both match to the same value, a value of y we're going to call y match in this limit. So that tells us C2 is a minus x1, a minus C1, which I can rewrite that way. And now if I plug in, I get my inner solution is now completely determined. Here is the complete inner solution. And notice that this part of the solution actually is exponentially small, except in the boundary layer region where x is between 0 and epsilon. And here's the crucial point, right? Alpha was greater than 0. Because of that, the contribution from the boundary layer goes to 0 as x becomes positive. If alpha were less than 0, the reason the boundary layer is on the right-hand side is because that behavior is reversed. With alpha less than 0, Instead, the boundary layer on the left-hand side, the value of the solution in the boundary layer goes to 0 as you go to the left of x equals 1. We can actually construct what's called a uniformly valid solution. We add the outer solution plus the inner solution. We expect the inner, and we subtract where they overlap, the matching region where they overlap, the value where they overlap. We expect that this inner solution, having subtracted the matching solution, is only valid is only useful near the boundary layer, and it's exponentially small otherwise. So we expect that having done this, we will get a good approximation to the solution everywhere. And here is the uniformly valid solution. We just add y outer, which is here, to y inner, and we subtract the matching solution. And when you do that, this is the result. So in the problem set, you'll actually look at an example. You'll do this example when a of x is less than 0 instead of greater than 0, and show that you can solve, but only if you put a boundary layer at x equals 1.